Denjo, you should send an WhatsApp to Ricardo, because there has been a time change in Dublin.
Oh, yes, I will send him an email.
You
Yeah.
know about it. Huh?
All right.
Okay.
It has been advanced by an hour,
Yeah.
so you should tell him at least.
I should have mentioned that in my thing, but
Okay.
Can you see the PDF?
Yeah.
Okay, perfect.
Yeah. Should we start?
Yep, I'm ready to start.
Perfect. Yeah. Thank you, everyone, for joining. It is my pleasure to introduce today's speaker, Evangelos Akianakis. He did his PhD in MIT and had a few postdoc experiences all over the place in Netherlands, mostly in Leiden and in Amsterdam, in Nijmegen. And he is now La Caixa Fellow in Barcelona. And he's going to talk to us about surprises in preheating inflation.
Thank you very much for the invitation and for the introduction. It's good to be here, even virtually. So today I'm going to talk about some work that I've done over a few years, an overview of the field. So okay, I will try to break it up into three pieces, because I don't know exactly if everyone's working on inflation or not. So I'll try to give an overview of why we think inflation is a good idea, then why we need reheating is a necessary idea, and then what sort of new ideas we have about realistic reheating scenarios. Okay, so let's start with introduction. So this is our universe, the way our cartoon picture of the universe. Most of our information comes from the cosmic microwave background radiation, obviously, right? This is the period of time when electrons and protons formed the first atoms, meaning that the universe became neutral, right? Well, the universe was neutral, but made up of neutral matter, in which case photons could propagate through this transparent medium rather than scattering off a plasma as it was before. And of course, as the universe cools, as the universe expands, it cools. So different types of interactions and physical processes become dominant. And I am mostly interested in the earliest parts of the universe, essentially in what set this thing to motion, right? Which believe it is inflation. So cosmology over the last few decades, I mean, cosmology, I would say, as the idea of what is out there, has been in the human mind since the beginning of at least scientific progress or scientific questioning. But in the last few decades, it has become an increasingly data-driven field. So 1929, we got the Hubble telling us the universe expands. 64, we got Penzias and Wilson discovering this afterglow of the Big Bang, right? The CMB. And this is a 2018 picture of the Planck satellite, giving us fantastic resolution of the inhomogeneity of the tiny temperature fluctuations on the CMB. So inflation is our theory, or our leading sort of paradigm for the very early universe, and it can be explained. It has, of course, you can explain it in multiple degrees of abstraction or detail. But okay, at the very basic level, what we define as inflation is an accelerated expansion of the universe, right? In that definition, dark energy is a form of inflation. So you could call dark energy a very low energy inflation. But as for the inflationary period that happened in the early universe, it is a very rapid accelerated expansion of the universe, meaning that the universe doubled around 100 times, right? In something that can be as small as 10 to the minus 34 seconds. Right? So it is actually a very violent sort of expansion of the universe. And what you gain by this, right, is that you can start with a very small homogeneous patch of the universe, then you blow it up by e to the 60, and then you can have the homogeneous universe needed to set up Big Bang. And this solves the so-called flatness problem, which means that if you count the energy budget of the universe, you find it extremely close to flat. And we know that if you start with tiny fluctuations from flatness, they grow over time, right? You start with a slightly closed universe, it will crunch immediately. Start with a slightly open universe, and the curvature will continue to increase. And inflation gives you, even at the very intuitive level, a way of explaining why we're exponentially close to flatness. The same way as an ant living on a balloon. If the balloon is increased by e to the 60, then the ant has no way of knowing the balloon has a curvature, right? The balloon surface will be exponentially close to flat at every point. Now, the next question is, how do you get inflation? Right? This sounds a very exotic, a very curious evolution for the universe to undergo. So how do humans do that? So a very simple way to do that actually is to propose or to postulate the existence of a scalar field called the inflaton, unimaginatively, which is rolling, which just has a scalar potential, right? So at the classical or the background level, a scalar field evolving in its potential is just the same as a ball rolling down a hill, right? So it's a very simple mechanics analog for what inflation does. And of course, because gravity is in the game, the universe expands as this ball rolls down the hill, and the expanding universe can be written down in the Klein-Gordon equation as an extra form of friction, this 3h phi dot. So this is it essentially for inflation. And just to give you also the red and the blue terms, why did I write them like this? So the blue term gives us the spatial inhomogeneities of this field phi. We usually assume that, and that's how inflation works, that you have the equivalent of a Bose-Einstein condensate, right? You have a coherent field all over space with tiny fluctuations. So if you don't care about the tiny fluctuations, you can set the blue term to 0, and you get what we call the classical or background motion of the inflaton. And on the next level, if you set up the red part, so the acceleration to 0, you get what's called slow roll inflation. And slow roll inflation is actually enough to teach you anything you need to know about how the inflationary mechanism works. So the bonus of inflation is that not only can it explain why the universe is homogeneous and flat, but the universe is not homogeneous, right? It is homogeneous on average, but it has galaxies and it has planets and people and physicists and the CMB, obviously. So inflation, essentially, you get fluctuations for free, right? You get fluctuations for free because, as I said, there's this blue term here. So there are some fluctuations of the field, and those fluctuations have to be there if we believe in quantum mechanics. So if you believe in quantum mechanics, every type of matter field has, is subject to the Heisenberg principle, meaning it has tiny fluctuations at the quantum level. And what inflation does effectively is it takes those fluctuations from the quantum and it stretches them to the microscopic. So as the universe expands, it stretches quantum fluctuations with it, making them big enough to be cosmologically relevant. So this actually allows us to calculate. So you take an inflationary model and you go and calculate what sort of fluctuations you get. And the simple way, so at the end of the day, we end up again with this beautiful CMB. So you see that the CMB has hot and cold spots, this red and blue. This corresponds to slightly bigger and slightly smaller temperatures than the average 2.7 degrees Kelvin. And we can go and do a Fourier transform or a spherical harmonic decomposition, right, to check the spatial correlations of those fluctuations. We define the so-called power spectrum of inflation as some amplitude times k to the ns minus 1. Ns is what we call the spectral index. So scale invariant perturbations would correspond to ns equals 1. And you would expect that it will correspond to ns equals 0, but for historical reasons, ns equals 1 is the scale invariant spectrum. Now, if you go and calculate, if you take a simple inflationary model, like the simplest thing we teach sort of undergrad, and you go and calculate brilliantly, you get perturbations that are largely Gaussian, and ns being very close to 1, but not 1. And if you go out and measure, you get perturbations that are very Gaussian, and ns being very close to 1, but not 1. So essentially, even the simplest inflation toy models you can write down have enough sort of explanatory power. The problem with inflation and why there are more inflationary models than inflationary physicists is that it's a paradigm. It's like QFT. So, QFT cannot tell you what the mass of the electron is, right? QFT cannot even tell you that the standard model is SU3 cross SU2 cross U1, right? QFT tells you if you impose SU3 cross SU2 cross U1, what sort of particles do you get, right? What sort of interactions do you get? So inflation is a paradigm for calculating, but you have to impose a model. You have to sort of propose or suggest a model. And usually the predictions of the models are put on this two-dimensional plot, which is a very kind of easy way of excluding models or testing them against data. On the horizontal axis, you have this n sub s, the primordial spectral index, and we see one is here, right? And the data are here. So it's really not scale invariant, but it is very close. It's like 0.96, 0.97. And on the vertical axis, we have something called the tensor scalar ratio. And this is actually the ratio of power in gravitational waves from inflation and density fluctuation from inflation. By the way, why do we get gravitational waves from inflation? By assuming that gravity is also somehow quantized, right? What inflation also does is it takes the tiny fluctuations in g mu nu, right? The gravitational waves at the quantum level and stretches them to cosmological proportions. Unfortunately, we have not discovered this R. So, and this is called the NSR plane. R eludes us to this day. All we have is an upper bound, right? It cannot be bigger than 0.07. You can see, there are several models that are already excluded, and this is not even a full catalog of models. But what you can immediately see is that every model is sort of shown on the plot by two dots, right? And the problem with the two dots is that there's an observational or the theoretical uncertainty that actually leads to these kind of two dots per model. So I will come now to where this uncertainty comes from, and this is the study of reheating. Again, this is where we're going with it. We know that somehow inflation generates the flatness and the fluctuations of the universe. The fluctuations.
Sorry, just
yes.
Your graph also had convex and concave above a certain line. What can you say what that meant?
Thank you very much. Yes. Well, convex potentials are phi squared and above, let's say. Concave are potentials whose second derivative is negative. So v prime prime positive or v prime prime negative, right? And v prime prime positive is ruled out.
Okay, thank you.
So anything that's phi to the 1 and above is ruled out, and we need potentials that look, plateau-like. Thank you very much. I mean, this is actually very important. It will come later to talk. Okay, yes. So yeah, as I was saying, inflation produces the fluctuations that embed themselves on the fabric of the universe. And during the cosmic microwave background radiation emission, right? Essentially, those fluctuations lead to a universe that is slightly inhomogeneous, right? So there are certain, in certain different parts of the universe have slightly different temperature, meaning the photons emanating from them are slightly hotter or colder. And I mean, it is amazing that we can even measure this thing, because what I say slightly hotter and slightly colder is 1 part in 10 to the 5. So it's actually, I mean, I admire the experimentalists for being able to do that. It's amazing that they can. However, there's another benchmark in the early universe, right? This benchmark is BBN. And BBN is I would say, a very strong, again, it's one more triumph of cosmology, of science in general, because we use things we test in the Earth, right? On the Earth, it's nuclear physics. It's the basic physics that runs nuclear power plants. And if we take the calculations that we do in nuclear physics and apply them to the universe, we can calculate that, assuming the universe indeed was in the hot Big Bang state, right? A hot thermalized plasma of standard model particles, then the ratio of helium to hydrogen should be that. And we go and measure, and lo and behold, the relation of the light elements is what nuclear physics tells you. So the BBN is actually a sort of fixed point in the evolution of the universe. The problem is how you connect those two. So during inflation in this flat convex potential, right? Excuse me. So inflation in this flat potential, right? You see V prime prime is 0. The field happily rolls and gives us inflation. And at some point it goes to its minimum and it starts oscillating around its minimum. Of course, this is the simplest way to write down an inflationary model, but necessarily at some point inflation must end, right? We're not inflating anymore. During inflation, the equation of state of the universe is -1. After inflation, assuming that the inflaton is some sort of massive scalar field, it goes to 0. And we know by BBN, the equation of state of the universe must go to a third, right? That is, radiation domination during BBN. We know that at some point we have to, so, okay, during this, if I only give you this plot, all the energy density of the universe is locked into this field. It is potential energy here, right? And then it becomes kinetic, mostly kinetic energy in the blue region. But again, we're not made of inflatons. So somehow the kinetic energy of this field must be transferred to photons, electrons, neutrinos, whatever, all the things that we measure and that we're made of. This is called reheating. So reheating is the process at which you take the energy from the inflaton and you transfer them to radiated degrees of freedom. By the way, it should be called heating, right? Because the universe is cold during inflation. But again, this is historical because the assumption was the universe was in some hot state before inflation cooled it, right? Or it was called the supercooling phase, and then it reheated. Anyway, historical remnants. Now, why is reheating important? Again, the problem is reheating can happen in a variety of ways, right? Reheating can happen immediately, so immediately or very soon you take the energy from the inflaton and you dump them into radiation mode. Reheating can happen very slowly, so you have a matter-dominated phase for a long time, and then right before BBN you reheat, or even there are proposals of sort of more exotic matter that gives you kination, so something dominated by the kinetic energy of scalar fields, giving you W bigger than a third. And the problem is that reheating, the fact that we don't know how the universe expanded during this period, messes up the mapping of the modes that are relevant, the fluctuations that are relevant for CMB fluctuations, to when during inflation they were produced. So again, it's exactly just trying to connect, trying to have a straight line from here to here, but you have no idea how the universe evolves in the meantime. Of course, the mapping will change. And in the CMB stage 4 science book, it was said many times, actually, I was impressed by how much they hammered down the point that the value of n star, n star is the point during inflation at which fluctuations were created, is not well constrained and depends on unknown details of reheating. And they say this as one of the major sort of roadblocks to making optimal use of next generation data. So if essentially you can look at this plot.
So presumably n is referring to the number of V foldings or
Perfect.
something.
Exactly, the number of V folds before inflation, whether it's exactly is this 50 or 60, exactly. So even if we squeeze this blue line, this blue circle more, it will at some point become comparable to the theoretical uncertainty. So squeezing it more won't tell us much unless we can get rid of this uncertainty. So okay, how can you dump energy from one field to another? We're particle physicists. The easiest way, write a coupling to some other particle, right? You impose or propose or suggest a coupling of the inflaton phi to some field, whether standard model field or some intermediary field, which will then decay into a standard model field or a dark matter particle or something. And then you go to your favorite particle physics textbook, you check the decay rate and you say, okay, the decay rate is blah. And when the decay rate is bigger than the Hubble rate, you say that this is when reheating concludes.
Sorry, Evangelos,
yes.
Question for your previous slide. So do we have any bounds on, does this somehow relate to the reheating temperature? And
yes.
Yeah, do we have any bounds on it?
Reheating temperature is when there are two things that, this is actually a very interesting question. So in the reheating community, we use the same word for two different types of things, which is bad. So some people, when they say reheating, they call reheating the time at which W equals a third. So the universe is radiation dominated. The other half of the community, when they say reheating complete, they mean that you actually get a standard model plasma. The two don't have to be together, right? You can first reheat, you can first dump all your energy into radiation in the form of a daughter field psi, f, whatever, and then those things scatter into standard model particles. So this is a problem, and so the reheat temperature as the temperature of the plasma of standard model particles, yes, it is. And it has to be big enough for BBN. I mean, I don't remember the exact number. I think you can push the inflationary scale all the way down to maybe even MEV scale, and then reheating is H times. I mean, as long as it's above GeV, I think you're fine. I mean, I don't remember the exact number, but because I worked on a low-scale inflation project recently, we had to really push it to say, okay, how low can we push it? But the only constraint you have is nuclear physics. As long as you don't mess up with nuclear physics during BBN, you can push inflation actually surprisingly low. I mean, the inflationary energy can be like MEV or GeV, and you can still get away with it. It doesn't have to be 10 to the -5 M Planck. And this is the distinction between sort of low scale and high scale inflation models. Good. So of course there is a problem, because physics is rarely obvious. If you talk about bosons, right? So if you want something to decay into bosons, okay, if you want something to decay into fermions, you are restricted in a sense by Pauli blocking. You cannot produce the same fermion you produced before, right? The same exact sort of quantum numbers. But for bosons, it's the opposite, right? It's the science behind lasers. It's more easy to, with lasers, it's more easy to produce a photon of the exact same wave number, right? If that photon already exists in your cavity. And after a few back and forths, all your photons are coherent. Same thing happens with bosons in preheating. If your inflaton produces a boson of a certain wave number, it's much more likely to produce another one. In mathematical terms, this goes under the name of Bose enhancement or Floquet theory. So if we write down, I mean, we just take some coupling of the inflaton phi to a daughter field chi. This is not important. I mean, the exact type of interaction is not important. And if we write down the wave number, the wave function equation for chi, we see it is of the form of a harmonic oscillator with a drag and a time-dependent frequency, right? So again, the easiest way to understand this is the child on a swing. We usually call it the child on a swing equation, right? When a child on a swing retracts and extends the legs, it changes the effective center of gravity of the oscillator. That changes the parameters of the oscillator, and that can actually, if they do it at the correct frequency, the amplitude of the oscillation increases. Now, okay, let's neglect the expansion for now and assume that the inflaton is exactly periodic, exactly sinusoidal. None of those things is correct, but it will turn out that to get intuition, it's perfect. Then we end up with this equation. Again, chi double dot, constant plus a sinusoid. This is called the Matthew equation, and it has been studied to death. But in general, an equation of the form x dot equals a times x, with a being periodic, right, has solutions of the following form: a periodic function times an exponential. And this exponential can be imaginary, real, or complex. Now, if it is real, we see that one solution grows exponentially, one solution dies exponentially. But it's this solution that we care about, right? So there are certain parameters that allow for this type of exponential particle production. I personally enjoy this analogy between preheating and solid state physics. In solid state physics, crystals are periodic in space, right? And since crystals are periodic in space, the electron wave function can again be written in this form, right? Floquet theory all over again. And in that case, the places where the wave function is exponentially decaying, these are the energy gaps, right? The disallowed regions, and the periods and the momenta when the wave function of the electron is the Floquet exponent or the block exponent is imaginary, then it's a traveling wave of electrons, and this is the valence and conduction bands. So it's exactly the same thing. The solid state physicist's energy gap is our particle production. And this is how we present this thing, so-called Floquet chart. The Floquet chart is usually a three-dimensional chart. One side is the wave number, one side is the strength of the coupling, and then we have the Floquet exponent. And you see here the size of the Floquet exponent for a simple example. And again, in solid state literature, these would be the band gaps. And we can read off the Floquet exponent, and if we go and check how a wave function grows, it grows exactly, you know, the blue is the numerical, and the red is the e to the Floquet exponent. You see exactly it follows this thing. And again, the introduction of parametric resonance to preheating was first pushed into the literature by Kaufman, Lind, and Starobinsky in the late 90s, right? And it was really a revolutionary idea at the time. There's another way of thinking about it, right? Another way of thinking about it, we again go back to our quantum mechanics roots, and we say, how do I calculate scattering of a potential, right? So scattering of a potential, we usually use what's called the WKB approximation, right? The WKB approximation means that as long as the frequency of my wave does not change much, I can write it as an exponential, right? E to the I integral omega dt. And of course, when the omega dot over omega squared is order 1 or bigger, the WKB approximation breaks down, and then I have to do the matching, right? And in the matching, I get reflected and transmitted waves. Same thing happens in preheating. So here I have an example. The orange line is omega squared. And the brown line is omega dot over omega squared. So you see, when omega touches 0, the adiabaticity is violated, and the wave function, which is the blue line, jumps. Right? So you get particle production in quantum mechanics terms, reflection and transmission, exactly at those points. And again, going back to solid state physics, you can analyze a lattice by saying I have an electron that scatters off many potential wells, or using block theory. Again, Floquet theory really nicely describes the situation, and you can also see the particle number in this case has discontinuous jumps, right? So every time omega squared goes through 0 or touches 0, then really you jump, right? You create particles. Of course, the universe is not static during inflation, it's expanding. So if we take the expanding universe into account, the numbers really change, right? But the theory remains. So we still get exponential particle production, you see here. But what happens is, as the universe expands, each mode travels through the Floquet band. So, you know, you get particle production here, then you don't, then you get particle production again, and so on. So it's more complicated, but the theory remains. So Floquet theory is a very important tool for studying these things.
Sorry, I have a question. So do you mind going back one slide? So with W going to 0, what does that mean for the inflaton mass?
This is not the inflaton mass. This is, remember, this is this. This is the, so imagine you have a coupling where G is negative, for example, right? K squared plus G phi squared sine squared can, so it's not the inflaton mass that goes to 0. It's the effective mass of the specific mode of the daughter field. So it's K squared plus the interaction term goes to 0.
Okay.
So yeah, so that's, thank you. And of course, for different, different types of interactions give you different, you can give you tachyonic preheating, in which this frequency actually goes negative, and then you get, I'll show you an example of tachyonic preheating later.
Okay, and just because yeah, sometimes I forget what the reason people name things differently. Why is it called preheating? So
parametric resonance from parametric.
yeah,
I think that's my understanding. It doesn't come before reheating. I mean, okay, there are two things.
Yeah.
I think just for parametric, but maybe it's just pre because it's the first stage.
Well, yeah, then you should be pre-reheating.
Yes, but I'm not in charge of naming things, and B, I think the people who are in charge of naming things haven't done the perfect job sometimes. So, you know.
Okay, but that's a very good answer. That I will remember. Perfect, thank you.
Okay. Good. So again, in anticipation of upcoming data, I come back to this. Why we care? Because different types of reheating can either last too long or be very quick, in which case you really get different durations of this period. Okay, now finally, the fun stuff. So I'm halfway through, and now we can actually go to something that's not from the 90s. So, okay, we talk to, I mean, I'm not a string theorist, right? Full disclosure, but whenever I talk to someone who is a string theorist, they tell me that the early universe must be a very crowded place, right? There must be a ton of scalar fields, axions and moduli, and they come from string theory compactifications, and sometimes from them they inherit couplings that go like e to the minus f d mu phi squared. So it is a very complicated place, right? So it's a pretty non-trivial leap of faith to say that, well, during inflation, there's one single light degree of freedom and everything else can be integrated away, right? I would say we would have to be very lucky if that is the answer we're looking for. So during inflation, right, from the early 2000s, people have started to really think about, okay, what if we do have more than one field during inflation? And what if we also have non-trivial kinetic terms, right? What if we have kinetic couplings in addition to the normal potential? And there has been a growing literature on the subject. And actually, in the last 3-4 years, there has been an explosion in new models where we have found new attractors, new dynamical attractors in even very simple models of kinetically coupled scalar fields that do not go along the potential gradient, but actually sometimes follow the isometers of the field space. So it's actually quite exciting when I have been deeply involved in this, but this is a talk for another day. I just wanted to sort of put it out as kinetic couplings are interesting during and after inflation. So now I will tell you the family tree of the work that I'm going to show. So in the 80s, we got inflation, right? In the late 90s, we got our first mention of preheating. In the early 2000s, field space effects started to be appreciated by the community. And in 2010, 8 and 10, two very important families of models entered the scene. In 08, Higgs inflation by Shaposhnikov and Bezrukov, and in 2010, αa-attractors by Andrei Linder and Ada Kalos and their collaborators. So my work has been to apply the field space effects in multi-field preheating. So essentially take preheating from the 90s into the 2010s, right? Do this, I mean, ideally do what Andrei and folks did for inflation back in the 90s. Okay, so now I will talk about both these families of models, right? I think I don't think I will need too much time, but again, if I take too long, just stop. What are αa-attractors, right? People will tell you αa-attractor is a inflationary model that has a hyperbolic tangent potential, but that's wrong. Alpha-attractors are models of inflation that live on a hyperbolic space, on a hyperbolic field space manifold. And the main drive for that is supergravity. So in certain constructions in supergravity, when you write down the Kähler potential, the superpotential, and then you go to this effective field, then you end up with these manifolds. Now, it's interesting that you can write a hyperbolic manifold in many ways, one very artistic way of writing it is this so-called Escher disk, right? And you see that the Escher disk has a finite radius from 0 to 1, right? But as you go towards the boundary of the Escher disk, you see more and more fish crammed there. So essentially, it would take you infinite time to reach the boundary of the Escher disk. Okay, so let's now write a two-field model of inflation on the Escher disk, right? You have the two fields, radial and angular, and this shows you the curvature of the, this shows you how the proper distance, and it actually tells you that it takes you infinite kinetic energy to move at the boundary, right? And the potential. So for now, which is contrary to this, so for now I assume that all the motion happens on the radial direction, and I'll forget about the angular direction. Which in certain constructions during inflation, the angular field can actually be stabilized to not move, right? And you really have a single field potential. Okay, so let me assume that in the angular direction, in the radial direction, I have a quadratic potential, because again, the first thing you try is writing down m squared phi squared.
Sorry, my question again. I'm just trying to understand a bit. So are you assuming that your inflaton field is a complex field, or that they're two separate fields?
Well,
or it's same.
It's the same thing. When you work with supergravity, you have complex. You have complex fields, so you cannot. That's why I always say that whenever you say the word alpha-attractor, it has to be multi-field. I try to really push the idea that you're not allowed to talk about single field alpha-attractors, because you have a complex field, you inherit it.
Yeah.
You cannot get away with it.
Okay. So now a stupid comment or question. As a particle physicist, the only way I can write two fields as two real fields as a complex field is that if they are mass degenerate. Is that an assumption you need to take here, or is this not relevant?
No. So no, you don't have that.
Okay.
Because the potential can be sort of quite arbitrary.
Yeah. Okay. Thank you.
It turns out it depends on what you say by what you mean by mass, because the mass actually at the bottom of their potential, yes, they are. Right, but during inflation, no, they're not. One is heavy, one is light. Right, but of course, when you would say particles, you probably mean, okay, around the minimum, right? And around the minimum, yes. In alpha-attractors, they are around, phi equals psi equals 0. Then the two fields are actually they have the same mass. I don't know if I have a plot here, but they do. At least in the alpha-attractor models that I'm aware of. Maybe there's a construction that can break it, but I'm not sure that if it can be done or not.
Okay, thank you.
Okay, so I assume I have a quadratic potential along the radial direction, and then I say, okay, I forget about my angular fields, and I have something that goes like dr squared over 1 minus r squared plus this quadratic, and I do a change of variables, right, to make this look canonical, the kinetic term. And then what I show is that the potential in these new coordinates give me this hyperbolic tangent potential. This is how the kind of magical hyperbolic tangent potential of alpha-attractors comes about, right? So we assume a quadratic, quadratic on the Escher disk. We assume that there's no motion along the angular direction. We do a simple change of variables, and we end up with this. And you see, this has exactly the shape we want, right? V prime prime is negative, so it's a plateau potential. Now, the beautiful thing with alpha-attractors is that they lead to what's called universal predictions, right? So ns is 1 minus 2 over n is n star, so we write down 60, and r is 12 alpha over n squared, where alpha has to do with the curvature of the field space. So essentially, they live on a vertical line on the, let me see if I can, right. They live on this vertical line, right? They're frozen in ns, and depending on alpha, you can hide them forever, essentially, right? from detection.
And why are they called alpha attractors? Why not alpha repellers?
Because because of the universal prediction. But essentially, I mean, even if you write another potential here, you would still get the same due to because all the magic is happening at the boundary of essentially what you can think of is any potential you can write down, you can expand it in a Taylor series. And this change of variables will pick up the first part of the Taylor series. So it will be tanh plus ... And inflation will only care about this, not the ... So essentially it's an attractor in parameter in model space.
And the larger your alpha is, the harder it is for your model to be proven experimentally.
Exactly. Yeah, with proven experimentally with CMB. Yes. Okay, so now there are multiple constructions for types of alpha attractors. Again, whenever I talk of an alpha attractor, I mean, these hyperbolic manifolds. In supergravity, we have, E model, T model, and even more, and then fiber inflation as a string compactification sort of idea. And here you actually see certain models on this parameter space, right, where ns can be 10 to the minus 2, 3, 4, 5, and so on. 10 to the minus 3 is essentially what we aim with CMB stage 4. So with CMB stage 4, we will get either discover something or rule out alpha attractors with small field space curvature, right? And we really have to be pushed below. I mean, it is annoying that you can hide them forever, right? Although, okay, I can discuss about some ideas to not hide them forever later.
Sorry, I thought you wanted in S to be around 10 to the minus 2.
Yes, NS. No, and NS is 0.967.
Oh yeah, 0.967. Yeah, okay. Oh, sorry. Yes. Yeah.
Yeah. So this, I mean,
S minus 1. I was thinking.
Sorry, it's probably a very bad plot. This is
no, I see it now. I see it now. Okay.
Sorry about that.
What is the time frame of CMB stage 4?
20. I want to say they start gathering data 2030 or so. 2027, I think, something like that.
Oh, okay.
I mean, I don't know. For these types of experiments, yeah, I believe both Lightbird and CMB stage 4 have tentative dates of 2027, 2028. With satellites, it's usually a bit worse. So I hope CMB stage 4 even maybe not optimal, but like maybe they do start in 2027 and say, okay, we will upgrade as we go and so on. Or maybe not all the telescopes start together, something like that.
Yeah.
And can you remind me what R was? What was the physics of R?
The R is the ratio of gravitational waves to.
Oh, I see. You're calling that R. It's a different R to the other potential one. Okay. That's fine.
Sorry. Yeah. Right. This is the R from the NSR plot.
It's the tensor. It's the tensor scalar.
Ratio.
Okay. Right.
Yeah. Sorry. This is the notational overload. At some point, you run out of letters. Good. Okay. So now let's look at what I think is an interesting way of thinking about curved manifolds. Let's say we have just a regular field rolling down a potential, right? So here you roll down a potential. This is a two-field model? Let's say you roll down a potential, and the mass for the vertical field is positive. So what will happen? The trajectories will converge. If you start here, 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 or here, they will all converge. If the mass is negative, the mass squared is negative, of course they will diverge, right? I mean, this is nothing new. Now let's look at the geodesics on a hyperbolic manifold. What do they do? Well, they diverge. So the geodesics on a hyperbolic manifold look like the trajectories of a tachyonic field. So there must be some relation between tachyonic mass and hyperbolic manifolds. Let's go and actually write down the fluctuation equations. Let's do some math. So the background, so the equation of motion for evolution on these spaces, the nice thing is we know GR, right? So essentially, those fields live on an internal curved field space. And how do we deal with it? Well, we define covariant derivatives. So essentially, we take what GR told us decades ago and we apply it to a slightly different problem. So whenever you see a time derivative, you write down a covariant time derivative, and the same thing with the potentials, and that's it. So it looks like the Klein-Gordon equation with a little complications. The fluctuations are slightly harder, but again, you can write them down in a similar fashion, and you get this effective mass matrix, which has now more components than before. It's much easier to analyze this if the background motion is a straight line, right? So if you don't get what is called turns in field space. So if, let's say, the phi field just oscillates and the chi field is a spectator. And this is actually what is true for our problems. So if we go along a straight line and we look at the vertical field, the spectator, then we can nicely quantize the fluctuations. We can write down the mode functions of the harmonic oscillator again. So this looks extremely boring, right? Why am I saying this? But the effective mass has now two components. The effective mass has one component, which is, again, field space metric and covariant derivatives, but this is a fancy version of V prime prime, right? Second derivative of the potential. And the second, and the brown mass here is a half field space Ricci times phi dot squared. And now we should look at this, right? So hyperbolic manifolds have a negative curvature, which means here is the tachyonic mass that I was alluding to before. Now, okay, if we go to an actual alpha-attractor model, I mean, I will not bore you with exactly the construction, it doesn't matter. The important thing is the field space Ricci scalar, R, goes like 1 over alpha. So essentially what alpha is telling us, I mean, alpha-attractors are quite cool because they tell us the amount of gravitational waves or the tensor-scalar ratio is related to the curvature of the field space manifold on which the fields live. So I mean, I find a very nice thing that there's a geometrical interpretation of a measurement. So people in 2018, a group in the University of Warsaw did some lattice simulations for preheating in alpha attractors, and they saw that they preheat very efficient. Yes.
Sorry, I just wanted to understand that a little bit better.
Yeah,
presumably, the gravitational wave spectrum is unaffected by, and when you're taking, or the amount of gravitational waves is largely unaffected. That's a gravitational aspect, and what's dominating it is the
well,
scale.
essentially what happens, it's not that, okay. So you can see it's not quite that. You can see here.
But this is just the scalar part.
Yeah,
so,
but okay, you can see here that V, right?
Yes.
The potential is multiplied by alpha.
Yes.
Mu squared is constant. And so what happens is that as alpha goes down, so as the curvature becomes more curved, the effective potential that you derive is lower, has a lower plateau, right? And gravitational waves, they are essentially de Sitter fluctuations, go like Hubble squared.
Yes.
So gravitational waves go like Hubble squared. You reduce the energy scale of inflation, you reduce the gravitational waves.
So even though you're increasing the curvature of space,
of internal space. That's internal.
It's an internal, yeah.
Yeah.
That's the. I mean, I agree. It's not. I mean, it's not intuitive in any sense. I just find it interesting. I cannot say that I could have, foresaw it. But this is. I mean, this is sort of a well-known fact of alpha attractors. But most of the time, I think we do not think about. I mean, most people, because most analysis of alpha attractors has been, we stabilize one field and we're done. I think a lot of that was I mean, essentially the first time we thought about preheating with a second field was 2018. Essentially, Christoph scooped me because I wanted to do this, but then we did the explanation. So he came up with the simulations first, but he didn't offer an explanation of why he was seeing that efficient preheating. I mean, he just said, okay, let's just put both fields and see what happens. Okay, so here's the interesting part. Actually, alpha attractors are fantastically simple and more simpler than I thought. when I started. So let's go to this, this squared effective mass, right? It's a half Ricci times phi dot squared. The Ricci of the field space goes like 1 over alpha, right? The field amplitude goes like root alpha, and you can see it from here, simple scaling. And the frequency, so delta t, goes like mu, because at small values of phi, the alphas cancel out, and you get mu squared phi squared. So essentially, 1 over alpha times root alpha squared, order 1. So the tachyonic mass of alpha attractors is alpha independent. So again, another attractor hidden inside alpha attractors. This means that and we were quite surprised when we saw that. So these are the Floquet diagrams of 3 different, the same potential for 3 different values of alpha, but rescaled in a proper way. So the vertical axis, we rescale phi naught divided by root alpha, and they fall on top of each other. So essentially, alpha attractors seem to have one universal Floquet chart at low alpha, right? Which means you can just compute one and estimate all the others. Because what happens essentially is the following. You get the same amount of tachyonic amplification per oscillation, right? But for smaller alpha, you get more oscillations per Hubble time. Just because the frequency of oscillations is the same and the Hubble period grows. So that's why as you go lower and lower and lower in alpha, you preheat faster and faster and faster. You get more tachyonic oscillations per Hubble time. So essentially, for alpha smaller than 10 to the minus 3, you preheat within fraction of an e-fold, so immediately. And this was, this was a very interesting explanation. Now we looked at different alpha attractor models that become a bit more complicated if you get other time scales in the problem. So if the potential also has a feature, but I don't want to go into that. It's a bit more, we're still trying to understand it better.
So wait,
Yes.
So what is the benefit of preheating happening faster is that you can have a smaller reheating temperature?
Bigger. No, essentially for preheating happening faster, essentially you don't have this uncertainty anymore. You know that you go into radiation dominated expansion immediately. So you don't say 50 or 60, you say 60. Essentially this thing, so you can imagine that thing as you go down shrinking to a point for small alpha. And that's also interesting because it's one of the ways of hiding them. At least you know that as alpha goes down, you cannot play with the shift to hide them, right? You cannot invoke the theoretical uncertainty. Okay, now the other big family of models is so-called Higgs inflation or Higgs-like inflation. The idea was first proposed in 2008 in a paper by Bezrukov and Shaposhnikov, and the idea is the following, right? We know there's one scalar particle in the standard model, which is the Higgs. We didn't really know it back then, but I guess we did. So let's see if the Higgs can give us inflation. Well, it can't, because for large values of the field, it's a 5/4 potential, and 5/4 potentials are ruled out completely. And if you try to use the Higgs as a hilltop model, then the fluctuations are off by orders of magnitude. So just taking the Higgs simply, which I think Alan's original idea was to use the Higgs for inflation, but the result was completely wrong. However, you can do a trick. Not a trick. You can invoke one more parameter, let's say, and the parameter is the so-called non-minimal coupling, right? So you can write a non-minimal coupling of the Higgs field to gravity, Xi h squared r. Now, the EFT allows it, and also, if you go to Birrell and Davis, you see that if you try to do an RG flow of self-interacting scalar field in curved space-time, this thing is generated as a counter term. Of course, in that case, Xi is not as big as we want it, but still this shows you that this is not a crazy term to write down, right? It's a necessary term of the theory. And again, lo and behold, NS and R are exactly the same as alpha attractors for alpha is 1. I mean, they fall exactly on the same spot, right? The interesting thing is that, again, let's go to single field motion. Let's assume you have a single field. Then you can always do a transformation, right? You can always do a field redefinition and turn a quartic field into a plateau potential. And okay, here's how you do it. So in the Jordan frame is the frame where gravity looks ugly. That's my definition. So in the Jordan frame, you have this non-minimal coupling and some fields and potentials. Then we do a conformal transformation, which is essentially the Mercator projection, right? We do for map making. And through that, gravity looks simple. And I like my graviton vanilla. So, however, this comes at a cost of changing the kinetic terms and the potential term. Now, the potential term goes from this 5/4. So here I took two 5/4 potentials, right? So from the 5/4 ball, it goes to a plateau potential. Right? And again, you can inflate along the plateaus of this potential. However, for two or more fields, there is no field redefinition you can do to make the kinetic term look canonical. So necessarily, this means that this Gij corresponds to a curved manifold. And this is actually the shape of the manifold. It's flat at large distances, and it has a spike at 0. Right. So this is exactly where preheating is happening. And actually, this is quite fun. The red line here, what we did is we turned off the potential, and we just initialized the two fields with some initial conditions, and we saw a slingshot, right, like you see around planets. So this is, this looks like general relativity, right? This really does the same as GR.
If I understand correctly, you're using a Higgs, it's the Higgs doublet here. That's what you're.
This is, here, thank you very much. Here I detached a bit myself from the Higgs. This can be any I will come back to the Higgs at the end. So just to, a lot of this work, because the Higgs has the problem that you know the parameters, right? You have to have the Higgs, you have to have the Higgs doublet, and so on. I will come back to the actual Higgs doublet at the end, but now I'm just saying I have two scalar fields with quartic couplings. So inspired by the Higgs, but not necessarily the Higgs.
Okay, and you're assuming one XC, one coupling to the curvature.
Two of them. It's XC1 phi
okay,
1 squared
yes.
plus XC2 phi 2. Thank you very much. Yes.
And you have taken that as your F of phi.
Exactly.
And you've done this this field redefinition for
exactly.
Okay, right.
Thank you very much. Yeah, I should have been clear about that. Thanks.
I have a question.
Yes, absolutely.
So you said then you can always get inflation to go along the plateau of the potential. How does that constrain you too much? Is that a condition you can always satisfy?
Yes. Not only can I always satisfy it, this is like a super attractor. It always will go there. Here we started. We just randomly took. We randomly took two field models, randomly chose potentials and initial conditions, and they always land in a plateau. All you need to satisfy inflation is that along the plateau, lambda over xc squared is 10 to the minus 10 to do the correct fluctuations. This is roughly, so, AS is roughly lambda over 12 xc squared. So all you need is this. Yeah, I wanted to call this a super attractor, but Dave didn't let me. And we even did it for 3 fields. And you see there's some craziness happening for one manifold, and then you really relax to a plateau, to one of those plateaus. So by the way, now we are doing this for, we have a code and we want to do it for 100 fields and see if then the distribution of parameters actually changes this picture. But yeah, this was the perfect question at the perfect time. Good. So again, the reminder of the effective mass, right? Blue and brown term, potential and field space. And again, the field space feature is when preheating happens. So during inflation, even if you forget about that, so all the Higgs inflation papers are correct. in a sense. During inflation, you don't care. After inflation, you do care. Okay, so let's look at the two masses, right? Forget the green term, it's relevant. So you get for small xc, this is the effective mass, and you see red is equal to blue, right? So everything is potential, which makes sense. This spike grows with growing xc, and it goes to 0 for xc goes to 0. Now for xc equals 10, what happens? The red and the brown are roughly equal and opposite, because one spikes at 0, one spikes at phi maximum, right? They're out of phase and they're roughly the same. This means that M effective squared never touches 0. So the adiabaticity violation here does not happen. So I expect actually preheating to be suppressed.
Just one xc less than one question on xc less than 1. There is nothing special about xc equals 1/6, the conformal coupling.
No, it's minus 1/6.
Oh, it's minus 1/6 in your notation.
In these definitions, yes, yes.
Yeah, no, okay, that's
it's
fine.
how you write it. Yes, thank you very much. Right, so then let's go to xc much bigger than 1, so 100. Then we see this picture. So we see that the effective mass is dominated by those spikes, right? Now let's see what we want, right? We want omega dot over omega squared to be bigger than 1 if we are to get a adiabaticity violation. And actually this happens. So before I sort of gave you all this analysis about how adiabaticity is violated when omega goes to 0 and then omega dot over omega squared is bigger than 1. Well, here is the exact opposite. Omega squared is huge, but omega dot is huger, right? So adiabaticity is violated through a novel mechanism which has no analog in sort of minimally coupled models, and also a broad range of wave numbers is excited. So you can excite particles with wave numbers or masses as big as xc times h. So in principle, you can create particles whose masses are bigger than the Hubble scale. Right? These are called Wimpzillas, for example, in Rocky Kolb's work in the 90s.
And if I might just go back again, since you've taken xc as to be negative, or relative to the conformal coupling, if I take xc in your definition to be negative, what happens?
Thank you very much. This is one of the things I wanted to actually look in more detail to. I believe what happens is actually the field space here. Okay, it depends. If I take one xc positive, one xc negative,
okay,
then this turns negative. Then I believe the field space at the origin goes negative. If I take both to be negative, I think the Ricci still remains positive because this goes like c squared.
Okay.
But this is one of the things I have been wanting to do for dark matter production. See if I can play with two different x's, one close to the conformal, one very big, and see if in that limit something interesting happens. So
and if just for my understanding, if I take both of them to be conformal coupling,
I think nothing happens there. I think there nothing happens.
Okay, yeah, that's probably what I would expect. Yes, because the G should be essentially irrelevant.
Exactly.
I have a question to your previous slide.
This is the
yeah. So is there an exact value of xc where the effect from these two?
Beautiful. Yes and no. In the static universe, yes.
Mm-hmm.
In the static universe, there's a magical xc in which the background is actually exactly sinusoidal, which is fantastic. I wouldn't have, and essentially then you don't see anything. However, for expanding, I mean, you see for the expanding universe, the two effect sort of redshift in a different way. So there's not an exact xc that completely washes it out, right? So that's it. So I mean, yeah, here you see I plot m over h, and it seems to grow because h essentially decays. The Hubble scale redshift. So here the linear analysis, xc equals 0, you get the Lamet chart from Linde's papers. Xc equals 10, you see the resonance band have pinched, right? So it's what you expect. You see almost no adiabaticity violation. For x equals 100, you see a dense forest of instability bands. So everything is unstable. Everything will, I mean, you get particle production everywhere across the board. And of course, yeah, I mean, compare this, for example, right, to this. And here we need lattice simulations to move forward. I mean, we spent 3 papers actually writing down the analytics, which was super fun, but then we realized, okay, you know, we need to really see if somehow backreaction shuts this off or whatnot. And here I have the lattice results. So let me guide you through them one at a time. Let me start at the upper left panel. We got a small xi and a large xi, so 10 and 100. And we plot what happens sort of without backreaction and with backreaction. So you see for x equals 10, particle production is minimal, right? You need to wait like very, very many oscillations to start seeing some shedding of energy. So nothing, it's boring. However, for x equals 100, which remember is this case, you see that the background inflaton decays within 5 oscillations. So, you know, 1, 2, 3, 4, 5, nothing. I mean, you siphon all the energy within a few oscillations. And you can see it here as well. Here I plot phi RMS and chi RMS is the red and the green. So you see that the secondary field gets excited every time you go through 0. This is exactly the same as this, right? So same mechanism. And at some point though, and that's the interesting thing why you need lattice simulations, it starts dragging the phi field with it. And at some point you see that the energy in phi and chi are roughly the same. And here you see the power spectra of the 2 fields. So in purple, you have the chi field, in solid, you have the chi field, in dotted, you have the inflaton. Initially, you only produce the daughter field. At some point, it starts dragging the inflaton with it. And at late times, you end up with something that looks like a thermal spectrum. So you essentially you immediately shed your energy into fluctuations, and those fluctuations seem to thermalize very quickly. And here I show a sort of an equivalent picture. This is the energy in fluctuations, so 1 minus the energy in the background. And you see that for small amounts of non-minimal couplings, you don't get efficient preheating. For large value of non-minimal couplings, you get efficient preheating. And also the W goes to 1/3. Right, so we see complete preheating and a quick approach to radiation domination.
Sorry, just
yes, absolutely.
I'm just trying to get it right in my head, because your number of e-foldings is now, you're starting your e-foldings
at inflation, at the end of inflation.
At the end of inflation, because it's not to be compared with your previous.
No. This is in this thing, like n is minus 60, and for CMB.
Yeah. Okay.
Perfect. Thanks. And actually, we were also very excited about this. Essentially, due to these non-minimal couplings, right? It seems like you can get a very short period of kination, right, where W is almost 1. We weren't able to prolong, because if you prolong this for a long time, you can get interesting things for like gravitational wave enhancement and stuff like that. But this seems to be a transient effect that we don't. I mean, I don't understand it extremely well at this point.
So
analytically, I mean, yes.
So it seems then large values of C are preferable. So yeah, I mean,
yes.
It's really good for Higgs inflation, but yeah, you're going away from scale invariance, right? I mean,
why am I going away from scale invariance? No.
I mean, well, C for the, I mean, conformal value for C is the -1/6.
Oh yeah, I'm going away for sure.
Yeah.
I mean, in terms of preheating and inflation, I do like large values of C, yes.
Mm-hmm. Okay.
And for let's circle back to Higgs inflation.
Mm-hmm.
So for Higgs inflation, we know everything. We know the couplings to W and Z bosons and Fermi. We know everything, right? So then we can actually calculate what happens. And here, and again, Higgs inflation is a multi-field system, right? So Higgs inflation, it's actually interesting you can actually forget about the W and Z, and then Higgs inflation is just a 4 scalar field system. But that's not 100% correct, right? Because you have W and Z bosons. And we actually, it was quite painful to do the conformal transformation in the SU2 cross U1 and write down the evolution equation for W and Z's. And you actually see that it's the longitudinal part of the W and the Z that gets excited. Okay, long story short, the red part is the mass of the W and the Z. And the blue part is this field space contribution. So you see it dominates completely, right? And it dominates, and you can see this M spike goes like C times H, and the W boson mass 10 to the 5 over root C times H. So for C bigger than 1,000, this is bigger than that, which means you get preheating, because this allows you to violate the adiabaticity, this doesn't, right? So you get very efficient preheating. How efficient? For Xi bigger than 10 to the 3 or so, you preheat within 1 oscillation. That's a bit cheating, because here we do it with analytical estimations, not with numerical simulation.
Mhm.
But it seems like the first time the Higgs crosses 0, all the energy is in W bosons immediately. So this is I mean, of course, this is quite important, because it means that it has a very large preheat temperature. So again, understanding plateau models can reduce the error bars in the NSR plot. And also, it allows us now to have a program, which we want to do, of taking the various extensions of Higgs inflation, like Higgs Caleron inflation, R squared Higgs inflation, and so on, and break them into 2 categories, regardless of the fact that at face value they might produce the same the same CMB predictions. Based on their efficiency of reheating, they can actually be broken into categories of high and low reheat temperatures, meaning one might have N60 and one might have N50. So we will be actually able to distinguish between them once the CMB stage 4 reduces NSR by, I mean, all we need is reducing NS by like a factor of 2, which is realistic for CMB stage 4, and actually breaking down this degeneracy completely on the theoretical level. So it's not pie in the sky. We actually do have, I don't know, 10 years maybe to do it, and we have started to go into that direction. Thank you very much.
Oh, that was.
I have some references.
Yeah, no, that was fantastic. Yeah.
Okay, yeah, thank you very much. Questions?
Yeah, I did go slightly over time, but not terribly.
Oh,
so.
yeah, we don't keep to the time. But,
that's great. Usually people start shouting and good.
There are probably some other questions, because I've been interrupting a lot. So
I've got a couple of questions.
yeah, Brian, please.
The Higgs scalar coupling that you introduced and it's reminiscent of Brans-Dicke theory. And my recollection is from a long time ago is that the magnitude of the coupling is quite restricted, because it leads to essentially a variation in Newton's constant.
Well, here
the psi can't be too. The coupling there can't be too large.
Thank you very much. Well, I think the trick here is that at the end of inflation, those fields disappear, right? So M Planck goes to its original value. I mean, Newton's constant is like
the usual Brans-Dicke constraints don't apply in this case.
I think so, yes.
Right, okay. And a second question is that, I mean, the reason Guth's original idea didn't work was because the Higgs coupling was too large. It led to fluctuations that were too large.
Exactly.
What is it the range of parameters here is such that doesn't happen? Or?
What do you mean original idea? Original idea, I mean without the non-minimal coupling.
Yes.
Yeah, with a non-minimal coupling, fluctuations are fine. Yeah, fluctuations are perfect. Are here.
Everything's under control.
Everything is yeah. I mean,
the fact that the force coupling doesn't cause a problem.
No. Okay. Let me be completely honest and say, show where all the bodies are buried. There is a question, of course, of why don't you? I mean, if you start writing xi phi r squared with a large xi, why don't you write xi phi r to the 4th, right? So there is a question of, okay, what happens if you if you start writing extra terms in the action. So we are playing a trick into introducing only the quadratic term, like C phi squared R, with a large Xi, which can raise questions about the sort of the validity of the theory as an EFT, right? In which, I mean, this is not my work in general, in most of my inflationary model building stuff, is not writing down models, but squeezing information out of models. So I take the model at face value and I squeeze all the information it has to give. But now, on the plus side, now we do have the tools to extend it. So there has been some work by Linde, Carlos, and Rust a few years back of writing down models of inflation like the Higgs, which include higher order terms in this non-minimal coupling. And actually, preheating can be very different in those models. I stumbled upon something quite interesting. But anyway, I don't want to go into details. All I'm going to say is that, yes, Higgs inflation in itself has problems, right? But we at least have the technology now that every term we write down as a correction to this pathological EFT, we can calculate it. I hope I
answered. And if I may, I have one further question. I presume you're using a Levi-Civita connection for the Einstein equations, is that correct? But if you take this h squared r Lagrange, and if you vary the connection and the metric independently,
you're going to portion. Yeah. So you're talking about kind of metric versus Palatini formulations.
Yes.
Thank you very much. This is also a very good. Here I take the metric formulation. You can do the same thing in the Palatini formulation, right? And you get different results. I mean, the Palatini formulation models are still compatible, and okay. I mean, actually, that is preheating is also it's efficient but slightly different. And actually, I'm working with a former student of mine to check to do this in the two models, essentially to check if you can distinguish between the two. Sorry, where am I? Sorry, give me 1 second to find the plot I want. Shouldn't take too long. Anyway, I'm trying to work to see if for example, the metric and Palatini formulations can be distinguished by how quickly they approach the attractor. So, for example, we know that in the metric formulation, you go to the attractor very quickly. And again, most studies on the Palatini inflation have been done for single fields. So we want to see the multi-field behavior of Palatini inflation and whether that can give a distinguishing feature between the two. So, but it is a very interesting question. Yes, thank you very much. I did not have any time to.
Thanks.
This former student of yours, Kaiser, is your former student?
No. Kaiser is, I'm his former student. Kaiser is my advisor now. So sorry, I'm saying we're trying to do the analog of this. Yeah. You know. I wish.
Other questions?
I have a bunch, but I'm going to wait until everybody else asks their questions.
Charles has flashed on. Are you on?
No, I'm fine.
Okay, sorry. I just have one physical question. Just if I understood your computations in the alpha-attractor case, it was essentially requiring, for consistency with observations, that the number of e-foldings would be around 50.
Okay, so give me 1 second. No.
Because the NS was 1 minus 2 over n.
Right.
And
so
you want about 2 over n to be around 0.4.
No, we want to be in here. No, it's actually closer to 60, 0.967.
Okay. Yeah. Okay. Then so and it implies the number of e-foldings is around 60. Is that what it does?
Exactly.
Okay. Physically, what scale do you start at with NS is equal to number of foldings 60? If I go back 60 from pre-inflation, okay, how small am I going?
You mean like length scales?
Length scales, yeah.
Yeah. I have to.
Strikes me that it's much smaller than the Planck scale.
No, I don't believe so. No. Well, it's the Hubble scale at the end of inflation, and then e to the -60 of that. So I have to do. I don't have the computation in my head right now, but that's. I did it once.
It's very small, though.
Well, it is, but I don't think it's smaller than the Planck scale, right? Well, the Hubble scale, the size of the Hubble scale at the end of inflation, we know what that is. I mean, we assume, let's say Hubble over, let's say 10 to the -5 and Planck. Oh yeah, I see. Right.
So it's around 10 to the -5 in Planck.
Right.
Which meant that quantum gravity had to play a role somewhere, which is
in the beginning. Yeah, sure. In the beginning of inflation, I would agree that we do have an issue of how inflation started. That is an issue we do have, right? But we have no. I mean.
Yeah, no. I just wanted to get the scales in my head correctly. Okay, so you are talking about starting these processes around 10 to the -5 of the Planck scale.
Yes.
Okay. I'll leave any further questions to the audience.
Well, I've got a couple.
Yes, go ahead. You're in.
But they're not very intelligent questions, but let me ask them anyway. So gravitational waves from inflation, what is their rough frequency? What experiments do we have that can?
Oh, okay. So the gravitational waves from inflation, the ones that we measure in the CMB, right? They're not measured through gravitational waves, right? They're not measured in Lisa or LIGO, right? So what they do is, excuse me. As a gravitational wave is propagating through the plasma, right, at recombination, what it does is it changes. So you can break down the modes, the polarization of the CMB in so-called E and B modes, right? And without gravitational waves propagating through your medium, you only have E modes. So you essentially deduce the gravitational waves that were of the relevant scales, essentially, of the horizon at recombination with the CMB. Of course, there are ideas for inflation to have some feature and be able to produce a spike in gravitational waves at some later times, which would be detectable in Lisa, for example, right? So there are models of inflation, but I mean, you need more bells and whistles, right? You need some extra field to talk directly to gravity, or you need some feature in the potential. You need to do something towards the last like 10 eFolds or so of inflation if you want to see them at Lisa, for example.
So when people say with, so the earliest picture we have of inflation is going to be at CMB, whether you use gravitational waves or anything.
Yeah. I mean, it's essentially it's like the first thing that exits, right, is at the CMB, and anything else will be later.
Yeah. Okay.
And the earliest things are the lowest L's. I mean, the CMB is the size of the universe, so anything else is. Yeah. So the interesting thing with gravitational waves is that we can essentially probe. So, for example, modes that would, let's say, something happens 10 eFolds before the end of inflation, right? That will enter the universe 10 eFolds after the end of inflation.
Yeah.
So, and it would be washed out. I mean, any density, unless you produce black holes, right? Anything else you would not see. However, gravitational waves would propagate until today, and you would be able to see them. So that's the thing, that it gives you a window. Gravitational waves give you a window into something that otherwise would be opaque.
Yeah.
And they would probe the later parts of inflation, not the earlier ones.
Yeah, of course. Yeah. Oh, and that would be observable with Lisa, for example?
It depends on the energy scale. I mean, then you go on a model by model basis, right? Because you have to see exactly, for example, we recently, I mean, there's even, okay, for models of inflation of energy scales 10 to the minus 6 and Planck or so, for models of inflation that produce R 10 to the minus 3-ish, or 10 to the minus 2-ish, then, for example, preheating typically produces gravitational waves, right? Because, you have a very turbulent plasma there, you produce modes, and everything is very turbulent, so you produce gravitational waves. Those are gigahertz. So those are, we can dream, right, of high frequency gravitational wave detection, and there have been proposals of resonant cavities and stuff like that, but then the sensitivity would have to be amazing to catch things from inflation. So those are sort of impossible. You can indirectly constrain them because gravitational waves are massless degrees of freedom, right? So you can constrain them through n-effective, because they do contribute to n-effective if you sort of produce too many. We recently actually proposed a not very complicated model of inflation that can produce gravitational waves at LISA or Einstein telescope frequencies from preheating, but then we need, we played a trick. We have a hybrid inflation model in which you have a field becoming tachyonic, and you couple it to a U1 gauge field through a Chern-Simons term. So it required a bit of, I can claim it's as natural as all other models of inflation, but all I'm saying is to get inflationary signatures at LISA, you have to work a bit.
Yeah.
So it's not if I write down a vanilla model that I give students, they will not do it, right? You need at least one feature that introduces this scale.
And if you do that, and for example, couple it to an extra U1, then would there be any other experimental signatures?
Very good. Yes, we wanted to have like a dark photon out of it, and then solve all the problems and go home. But it's very hard. We can't get the masses to. We wanted initially the original photon. It doesn't work.
Yeah.
Unfortunately, pesky standard model. And then we wanted to see if that would be some sort of dark matter candidate, or have some dark sector that does the trick. It seems hard. So we wanted this second inflaton to be like an axion and talking to it. Yeah, we wanted to do it as minimal as possible. But right now we have a paper out which has sort of squiggly line calculations, right? So linear analysis and so on. So we want to do some, we're gearing up to some more heavy numerical simulation, and then maybe things move around by order 1 or even an order of magnitude, and that might help, right? That might actually allow us to have correlated observables like, you have a leftover axion or a UN or a dark photon that you can somehow indirectly detect. But I don't want to say that it is.
Okay. This is something you and I have to have a discussion about, because I've got an idea that we might be able to make it work. But yeah, let's not exhaust other people with it. Just one last very, very naive question. So you keep on talking about what you can use from condensed matter physics to learn about inflation.
Intuition mostly.
Yeah. Do you think that anything, I don't want to say experimentally from condensed matter physics, but do you think there could be, I don't know.
Yeah,
you know what I'm getting at.
Yeah. One idea that I would love to do at some point. I would first need to get tenure before doing that, because I think that might take forever. But for example, there are all these ideas of like simulating analogs. So I would say, can you simulate a cosmic string or bubble wall collisions in some condensed matter? I think that would be doable, because condensed matter experimentalists are fantastically smart.
I know. Yeah.
They are mad. They can do magic things.
Yeah.
So this would be something that I would be very interested in, to see if you could create some cosmic string in the lab using with some material that has some U1 effective gauge theory inside it and stuff like that. I think that would be so preheating in some sense. You can do, maybe even something that, gravitational waves would be phonons, and you have some scalar, effective scalar field, and preheating would be, phonons would be the equivalent of gravitational waves. Some analog of that
Yeah.
Yes, but I think it's, it wouldn't be quite an endeavor that it would take like, a few years before it gives you something.
Yeah, Basel would be the perfect place to do it because they have a, good. Because we both interviewed for the same job in Basel. Fantastic. Yeah, that's all of my questions. Yeah.
Thank you very much for a fascinating talk, and
Yeah.
Thank you very much for having me here. Yes.
a lot of
Yeah.
insight into what's going on in this
Yeah.
field, which looks like it's evolved a long ways. I'm going to stop the recording
Okay.
if that's at this point. Just